14.13. We've seen in previous sections that the strength of an acid is indicated by its value of Ka, and the strength of a base is given by its value of Kb. For a conjugate acid-base pair, the two equilibrium constants are related in a simple way that makes it possible to calculate either one from the other. To illustrate, let's consider the conjugate acid-base pair NH4 plus and NH3, where Ka refers to the proton transfer from the acid NH4 plus to water, and Kb refers to a proton transfer from water to the base NH3. The sum of the two reactions is simply the dissociation of water. So the net ionic equation would be 2NH2 liquid yielding H3O plus aqueous plus OH minus aqueous. And by doing that, you multiply H3O plus, so that's like Ka, and times Kb, or OH minus. The equilibrium constant for the net reaction equals the product of the equilibrium constant for the reactions added. Ka times Kb equals Kw. What we've shown in the particular case is true in general. Whenever chemical equations for two or more reactions are added to get the equation for a net reaction, the equilibrium constant for the net reaction equals the product of the equilibrium constants for the individual reactions. So the K net equals K1 times K2 times K3, and so forth. For any conjugate acid-base pair, the product of the acid dissociation constant for the acid and base dissociation constant for the base always equals the ion product constant for water. Ka times Kb equals Kw. As the strength of an acid increases, meaning it has a larger Ka, the strength of its conjugate base decreases, having a smaller Kb. Because the product, Ka times Kb, remains constant at 1 times 10 to the negative 14th. The inverse relationship between the strength of an acid and the strength of its conjugate base was illustrated qualitatively in Table 14.1. Taking the negative base 10 logarithm of both sides of the equation Ka times Kb equals Kw gives another useful relationship. Pka plus Pkb equals Pkw, where Pka equals negative log Ka and Pkb equals negative log Kb, and Pkw equals negative log Kw, equals 14 equals 14 at 25 degrees. Complications of the equation of the equilibrium constant, such as Appendix C, generally list either Ka or Kb, but not both, because Ka is easily calculated from Kb and vice versa. Similarly, pKa can be calculated from pKb and vice versa. So pKa equals 14 minus pKb, and pKb equals 14 minus pKa at 25 degrees. Similarly, Ka equals Kw divided by Kb, and Kb equals Kw divided by Ka.